Hello, and welcome to my presentation on the mechanics of building and debugging for Unreal Engine C++ game developers. The purpose of this presentation is to cover some aspects of the build process of an executable in C++ and the lower level mechanics of how debugging works, all in the context of working with Unreal Engine, specifically on the C++ side of things. I wanted to make this presentation to concentrate some of this knowledge into a single centralized place, because I believe it will be useful to game developers who may not have formal programming training. And I think it's important to have a foundational knowledge of how executables are built, how a debugger is able to perform its role, and why debuggers are so useful to developers. Learning about the process of debugging is actually directly linked to many other parts of the process of creating programs as a whole, and gaining familiarity with it will also help you to better understand some of the errors and feedback you get from the build process when you're creating executables. This knowledge is going to apply to both Unreal Engine C++ and general C++ programming as well. So let's go ahead and get started. What is a debugger and why should we use them? My definition of a debugger is simply this. A debugger is a tool that is specifically designed to help developers find and fix issues in their code. A debugger can be either a standalone program or part of an integrated development environment, which is known as an IDE. For all of us working on Unreal Engine C++, we'll primarily be using an integrated debugger that comes bundled with Rider or Visual Studio. As for the benefits debugging provides, debugging is your most powerful troubleshooting tool as a programmer. Debugging allows you to inspect the execution of a program line by line, which in turn lets you track the flow of the code, which just means the paths that your program takes during execution. Debugging allows you to analyze the values and states of variables while a program is running, and all of this contributes to helping you identify errors or unexpected behaviors in code extremely quickly. Another useful benefit of debugging is that it just forces you to look more closely at your code, which in turn makes you more familiar with it. You might be surprised how you could write a program but not be truly familiar with all of its functionality, but this absolutely can and does happen pretty often, especially in the context of following a tutorial where maybe your level of knowledge is not equivalent to the instructor, but you're trying to learn. A lot of times that results in you write a bunch of code, but you may not fully understand exactly what it does. So using the debugger to step through your code really helps to tie the big picture together, formed from all the small elements that make up the program. Just in case you're unfamiliar with the term step I just mentioned, it just means to press a button in the debugger controls that will run a single line of code at a time when you're running your program in debug mode. Stepping will be thoroughly explained and demonstrated in a later video that will cover debugging controls as well as some live debugging examples. So we've established the basics of what debuggers are and what they do. In order to begin understanding how they work, the next step is to discuss a mechanism known as a breakpoint. A breakpoint can be thought of as a flag or a designator that you can toggle on a specific line or on multiple separate lines in your code that allows you to choose where the execution of a program will pause. When the program execution pauses on a breakpoint, it acts like a snapshot in that moment of all data currently being processed. And this is what enables you to inspect the state of the program, any variables in your current scope, and the execution flow of the program at that specific moment. So breakpoints are typically just a stop sign for the program execution, and that meets the need for the majority of use cases, but they can also have embedded instructions in them as well, which enhances their capabilities. This is a screenshot of the Rider Breakpoint Management panel. Both Rider and Visual Studio have a panel like this that allows you to view and edit all your breakpoints in a single location, so that's really nice convenience. So on the right there, you see all the conditions. The condition checkbox is one of the most useful features. By checking this box, you can type a code expression, for example, something like a Boolean condition such as x is greater than 5. And then the breakpoint will only stop the program if that condition is true when the point of execution reaches it. The log option is also a nice feature. Using this, you can print some text to the debug console when the breakpoint is hit, and it can print values as well as normal strings. The suspend execution option is also sometimes useful. Used in conjunction with the log option, you can make it to where the breakpoint doesn't actually stop the program, but will still trigger that data to be logged when the line the breakpoint is on is executed. And then the enabled option is sometimes convenient to allow you to just temporarily disable using the breakpoint to where the debugger will ignore it if it's disabled, but then you can easily re-enable it later on by just rechecking the box. You can modify normal breakpoints to be conditional breakpoints in all modern IDEs. So it's just good to know that the feature is there in case you run into a situation where it can be useful. Here's a quick animation of what it looks like to set a breakpoint. The region on the left next to where the line numbers are in an IDE, you'll usually hear that being referred to as a gutter. It's just an area that is typically used for small status indicators and other things like that. In this example I'm showing you here from Writer, you can see that they used it for some icons that give you some information. The little icon with the two arrows is just a convenience thing Writer adds that lets you, if you click it, it'll go to the declaration of the function, so it'll just jump to the header file. So clicking in this area, or sometimes on the line numbers themselves, that's how you set breakpoints in any IDE. So for this specific case, for Writer, you click on the line number itself, and once you see the red dot there, then that sets the breakpoint. But now here are the questions that we need to ask ourselves before we move further. How do IDEs or debugger programs know that enabling this red dot will cause a program to pause in debug mode? And how do they know to correlate the line you chose with the program after it's built into an executable? And when you're debugging and you tell the debugger to step into a function, how does the debugger know where to go? For example, if you look at my animation here, when my program stops on the breakpoint that is placed on line 126, and then if I click the button to tell it to step into the function, how would it know that going from line 126 where it calls perform interaction check should jump down to line 130 where the body of the function is? So we're going to answer these questions, but in order to do so, we need to examine something that happens during the build process of an executable. The answer lies in what's called a debugging symbol. To understand what a debugging symbol is and what role it plays, we first need to have a general understanding of the build process of a program. When you hear the common phrase in the programming community, build, as it pertains to code, it's actually a summary term that's referring to a very complex chain of events that results in an executable program. Building is actually made up of these four main stages: preprocessing, compiling, assembly, and then linking. Each one of these stages can be an area of study all on its own, so I'm only going to be covering them at a high level. As you know, we always start with a CPP file, which is the code that we have written. When we initiate a build, the first thing that happens is the preprocessor runs on all of our CPP files. The preprocessor handles all preprocessor directives in the code, which are the instructions you normally see preceded by pound signs like pound include and pound define. During this stage, those instructions are actually replaced with other code. For example, when you write pound include, that's telling the preprocessor to copy the entire contents of the file you've included into your source file. This is why includes are always at the top of a file, because we must always ensure that things are defined before they're used. So you put them at the top of your files above the bodies of your functions to ensure that. This is also why it's strongly encouraged to use for declarations as much as you can and only ever include what you need. Because for everything included, all of their includes and all of the includes in each one of those includes, the entire chain all the way down is copied into your file until there are no more includes. So the more includes, the more overhead that is incurred by this process, resulting in longer builds. It adds up over time. The end result of the preprocessor stage is .i files. This information is specifically focusing on the MSVC toolchain, which is what is used by Rider and Visual Studio for builds. Other compilers may handle their preprocessor output differently, but for our purposes, the .i file represents preprocessor output. In the next stage, the compiler runs using the .i files as input. The compiler is the stage we're likely all more familiar with. This is where code syntax and many other things like usages of variables and functions are all checked. So this is the most frequent source of errors when building because syntax mistakes are more common than other kinds. The end result of compilation is assembly language for whatever platform you're building on, and this is typically output in the .asm file format. After compilation finishes, the assembly phase runs. This takes the assembly code that was generated by the compiler and uses it to generate what is called object files. To use a simple analogy, you can consider object files to be the machine code building blocks of executables, hence why I felt the cube icon was pretty fitting here. Something I want to point out is that these three stages, preprocess, compile, and assemble, are run for every single source code file in your program separately. This should help to give you an idea of how a build can take a long time. If you have a slower processor or a ton of source code files that all have lots of includes, these stages must run on every single file in order to generate an object file for each one. The benefit we gain from this is that because the process is incremental and runs on every single file, if one single file changes, there's no need to rebuild the entire project. The system keeps track of which things have changed and which haven't, so if you do a full build, go back later and modify a single file, and that's the only thing that's changed, when you rebuild, only that object file gets rebuilt, and so it saves you a lot of time. The final stage in a build is the linker stage, and it's probably the most important. A linker is a tool in the C++ build process that combines multiple object files into a single executable. It resolves references between the object files by matching function calls and variable usages with their definitions, and it handles address allocation for the code and data used in the program. For example, if you have a character class and it needs to call a function in an inventory class, the linker is what's responsible for ensuring those two separate classes have a path to be able to interact with each other. So the linker is extremely important because it's what ensures that all components necessary for your program to run are correctly connected and present. Linkers are usually separate software utilities that are invoked by the compiler during the build process. And so because of this, they can have their own special configurations to enable custom behavior applied to them as well. And that's something we'll cover here in an upcoming slide. So the linker gathers all the object files generated from your program, and then it reaches out into your file system to gather any external object files that are needed by your program. A good example of an external object file would be the C and C++ standard library object files. You don't write them every time you write a program, so they must come from somewhere. They come from your file system on your machine, and the linker is responsible for gathering the objects needed from them for your program. So it's important to mention here that the linker will only try to gather the minimum amount of code necessary to complete the build process. So everything I've mentioned about the linker stage thus far applies to how it works with static external libraries. And what this means is a static library has all the code present on your system, and that code can be copied directly into your program as necessary during the linking phase. But there are also DLLs to consider, which stand for Dynamically Linked Library. The topic of DLLs can be an entire video on its own, but here's a really brief summary of how they work as part of the build process. When the definitions of functions in a header you include are stored in DLLs rather than in static libraries, the DLLs are totally external to your program and its build process. So the definitions of the functions that come from the DLL will be annotated as such, so that the linker knows they're external to your built program. So when it encounters one of these, it creates a placeholder for them that's what is known as a stub or a stubbed function, so that the build process can actually finish without errors due to missing functions. The assumption is made by the linker that the definition of those stubs will then be loaded at runtime from the associated DLL. And so that's why the DLL has the D in the name. By dynamic, what it means is it can be linked at runtime. So this is why at one point in your life using computers, you've probably had a program fail to start due to a missing DLL. The program quite literally depends on the DLL to find some of its missing code in order to run. Now, once all the necessary object files are gathered and all the pieces and parts of the program are able to be defined, they're then linked together to form the final build product, which is your executable. Then, when you launch your executable, the operating system loads any necessary DLLs during runtime in order to connect those stubs with the real code. So now you may have wondered why there's white dotted lines around the .i and .asm files. This is because they represent temporary output that is used but not saved by default during the build process. These files fall under a category of file related to the build process known as intermediates. MSVC does not store the intermediate .i or .asm files that are generated as part of the preprocessor and assembly stages by default, but there are other kinds of intermediate files that are saved by default. This is why you may have noticed that when you build an Unreal Engine project, your project folder gets some additional directories added to it, among which is the intermediate directory, and then there's the binaries directory and a few others. The .i and .asm files are able to be saved, but doing so requires configuring some specific compiler flags. If you aren't familiar with that term, I'm going to cover it in more detail shortly, but compiler flags is just a generic term to represent different command line options and arguments that can be set to control the behavior of the compiler in different ways. Object files from the assembly process are always saved by default, and so those can always be found in the intermediate directory after a build is finished. If the flag is enabled to save the .i or .asm files, then those would obviously show up in the intermediate directory as well. Binaries refers to the finished executable files that are generated from your code, and they are called that because executables are in a format consisting of machine-readable binary instructions. And those instructions is what is directly executed by your computer's processor. I now want to use one of my actual Unreal projects as an example to demonstrate some of the concepts I've discussed here. So this is a project I've titled CS Tutorial. It's one that I use for another series of videos I'm making where I demonstrate how to create an RPG inventory system from scratch. So if that sounds interesting to you, definitely feel free to check it out. And so I've just done a rebuild of the project from scratch so that we can look into the intermediate directory and see some of the outputs. So if I go all the way down into the directories, you'll notice there's quite a few here, but it's because there's different configurations that are accounted for in different build modes. I'm going to be discussing that a little bit here coming up when I talk about build configurations. Once you finally find the output for the build that you did, you'll notice that right away we see object files. So as you can see, there's only one object file. The reason for that is that the system is smart enough to combine all output from the assembly phase into a single object file when they're all built at the same time. Now I'm going to make a quick modification to the project by just adding a print statement to my character class, and then I'm going to rebuild and we'll see what happens here. So the build just finished, and as you can see, the game module object file is still there, but now when we look down here, there's an additional one for the character class. The system recognized that only a single file had changed in the source code, so only that object file pertaining to it needed to be regenerated. Now, if we go back to the project root level and we look into the binaries directory, All the information I've covered thus far has pertained to the build process in a generic way, as if you were building just a normal executable. Unreal does do things a little bit differently. We don't have an executable here because when we're developing, when we launch our game, we're not actually launching our game as a standalone project. We're launching the Unreal Editor and it's loading the data from our game. So by doing a build before launching the editor, the only thing that you will have is a DLL. Because just as I described the build process, how it relates to DLLs and loads things at runtime, Unreal Editor does the exact same thing with our game. So it uses a DLL from our game to understand how to load what it needs to. And some of these other files, the target, modules, etc., all of this contributes to being able to get all the asset references, the source code, and everything that's needed for the Unreal Editor to launch and load our game. When you package your game, that's different. That is where you're actually creating an executable for a target platform that's meant to be run standalone or with, minimal supporting files. But it doesn't use the editor. So in that case, packaging a game is what generates a standalone executable of your game. So now we've summarized the basic build process, but this still hasn't shown how exactly it relates to debugging and debug symbols just yet. So we're going to answer that, but first we need to take a look at build configurations. Build configurations are pretty much what they sound like. They're used to configure different options for your project that control things that happen when it is built, and this in turn affects the output of the build process. So build configurations just provide a more user-friendly way of setting different options such as the compiler flags I mentioned that allow control over the build process in order to build your executable in different ways. The alternative would be you would have to create a command line for building and modify it every single time you wanted to change something for the compiler and linker, and use that anytime you wanted to modify your build process. In an IDE, to choose the build configuration being used, it's as simple as switching a configuration setting because they usually come with several pre-made templates, typically debug and release at a minimum. But you can also create new configurations and customize them as much as you like. So the images on this slide are showing the build configuration panels in both Writer and in Visual Studio. The one on the right is actually a screenshot I took from the Microsoft documentation on build configurations, which if you're interested in, you can just Google Visual Studio build configurations and find lots and lots of information on them. But the main thing I want to illustrate here is that the overall concept will be the same in any IDE. There are menus to create, choose, or configure build settings and different compiler options for each project. You've probably at least heard the terms release build and debug build before now, but a high-level summary of those is that a debug build generates your debug symbols, and it also generally removes optimizations, while a release build does not generate any debug symbols and typically performs at least some optimizations. What I mean by optimizations is that they're just actions taken by the compiler behind the scenes to try to make your program faster, more efficient, and smaller in size. So I'm here in Writer now, and I wanted to be able to show an example of what a build configuration looks like. This is not an Unreal project. This is just kind of a little project I use for learning and experimenting whenever I encounter something I want to try to figure out. And so you can see that I even titled it learning.cpp. This was just something where I was testing out some stuff with pointers and references. But now if we go up here and look up here, you have a hammer, which is the initiate build button. And then to the right, you have a drop down. The drop down is where we choose our build configurations. And so you can see, I didn't create any of these. These are the templates I was mentioning. By default, this simple little project created a debug and release configuration, and then it allowed for 32-bit or 64-bit platform builds. Now, if I want to actually modify what those configurations do, in order to do that, I have to come over here. Now, the solution is called experiments, but a solution can contain multiple projects. So I have lots of different little code projects in here. So this one's called learning. If I right click this and then go to properties, this is where I actually modify these configurations. So you see, I still have all the same ones that were available in the dropdown. But now if I come through here and click on these tabs, I can modify different things for how the compiler and the linker behaves. Here's a section for the preprocessor. Here's some optimization stuff. And so you can see that there's just a lot of things you can configure. It's pretty complicated. Most of the time, you won't need to do this unless you know exactly what you're after. You can usually trust that the defaults are configured in a way that's beneficial to you. The main thing I wanted to show here is just that this is how you modify them. And this will be very similar. It's not going to look the exact same, but it will be very similar in Visual Studio. And we can see what I meant about the differences between release and debug. So if we look in release and we go to the C++ section, see under optimization, it's set to maximum to favor speed because you want your program usually to run as fast as possible. You'll notice they have options here for favoring size as well to make your program really small, which could be useful for, say, microcontrollers, like if you want to put something on a Raspberry Pi. When we go back to debug and we look at that under optimizations, you'll notice it's completely disabled. And I will explain exactly why this is shortly. So some of you may have been curious why I chose to use a non-Unreal project to demonstrate editing build configurations. The main reason for this is just that Unreal uses a slightly modified version of the build process, specifically when it comes to being able to configure the different build options. You'll notice if I go to the dropdown, it looks exactly like the other one did. We have debug game, development, and shipping, where shipping is pretty much the same as release. We have a few different targets, and then we have our platforms. But now when we go and open by right-clicking our project and look at the properties, it looks different. There's a lot of tabs missing. The reason for this is because Unreal uses C# on the back end to manage the builds. And that's why when you expand the source folder in your project, you'll see you have these .cs files that are for the project itself and then running it in the editor. Opening one of these, you can see that it pulls build settings, include order, and other things from whatever this parameter is. So that could be something that'd be worthwhile to investigate in a later video. But the main thing I want to show is that because it uses C# to manage that, it's a little bit different. So we don't get those compiler flag type options exposed to us directly. One more thing to show about this is if you open the build.cs file in your source folder, you'll notice it has this dependency module names here. These are the exact same thing as what I talked about on the build process slide where I mentioned external library object files. You can consider these to be external libraries to your project, except in C# style, they're called modules. But these are pre-made modules that come with the Unreal Engine source code. And when you need one in your project, you have to come in here and add it to this list so that when the linker runs, it knows to examine everything in this list to try to find any definitions that it might need. So at the end of the last slide, I had said that I did not specifically address how the build process related to debugging. But now you know. The build configuration determines whether or not the build generates the debug symbols and the other information necessary to debug the executable. But now we still have to define exactly what a debug symbol is. I'm going to define exactly what a debug symbol is and what is contained in it. But for right now, all you need to know is that it is the output from the build process that allows you to debug. So before we get into what it contains and what it is, we're first going to make a small adjustment to the build process diagram to illustrate when they're generated and what role they play in it. So when we say debug symbols are generated, what we're actually referring to is a file type called a PDB file. PDB stands for Program Debug Database, and you might also see it sometimes referred to as Program Database. PDB files are generated during the compilation phase alongside the assembly language, and they're only generated when building in a debug configuration, which we now know depends on certain compiler flags being set to tell the build to generate the debug symbols. When building executables for Linux, all necessary debug information can actually be embedded directly into the executable. So Linux doesn't use PDBs for debugging, but for Windows, this is not the case. In Windows, all debugging information is always stored in these separately generated files in this manner, and then these PDB files are then kept alongside your built executable to allow your IDE to find and use them. The way that your IDE finds them is that the name and the path corresponding to each PDB file for each source code file is embedded into the executable when built in a debug configuration. This is what then allows the debugger to locate the PDB it needs for debugging the program. It simply reads that embedded path information to find the associated PDB for a section of code. The stage of the build process where the PDB paths are embedded is the linker stage. When all the object files are being linked together, it also brings in those paths and links them into the built executable. PDB files are generated when we build our C++ projects in debug config. But how does this work for when you install Unreal Engine on your PC? If you install it via the launcher, you're not going to be building it from scratch, so you're not building PDB files. But we still have the capability to debug Unreal Engine source code when we install it from the launcher. The answer to that is when we install it from the launcher, we're installing one specific version of Unreal Engine. So the PDB files that correspond to that specific version are pre-compiled. And this is why you have to enable installing them in the engine installation options. To show this, if I go into my program files directory on my computer and I go into my engine installation, if you go into the engine directory, you'll notice that there's some actually pretty similar directories to what we normally see in our projects. We have plugins, intermediate, we have build, we have config, saved, that's another one. Now we also have binaries. So if we go into binaries and we look under Win64, you'll notice right away that for every DLL, which we now know contains source code that's used at runtime, for almost every DLL, we have a corresponding PDB file. Because we installed Unreal Engine 5.4 specifically, we get the PDB files for Unreal Engine 5.4. If we were to build the engine from source code, then we would be generating those directly from that build. So for instance, some companies, if you've heard of the game Satisfactory, it's a factory builder game that's pretty cool. I know from reading their devlogs that they've made custom extensions and modifications to Unreal Engine in the past to be able to suit their needs. So for an example like that, you're going to be building the engine from source because you have to be able to modify it. So you'll be generating PDBs when you build from your custom modified source build. Because we're installing just this one version, we have no need to do that. In fact, all the source code files are read-only, so you shouldn't be modifying them. But the benefit of that is that we can just then install the PDBs and begin to debug right away because they're all pre-made. So now we know that we build in debug config to ensure that we get debug symbols, which are in the PDB format, and then the information necessary to find them is combined along with all the different object files in the linker phase into the final executable. The final step we have to take before we clearly define a debug symbol is to first look at the term symbol that I've been using. In the context of programming, the term symbol is a generic term that represents anything symbolic for an underlying piece of information or memory in a programming language. So things like variable names, function names, class names, and even keywords like if or new or return All of these things are symbolic abstractions of either assembly language or memory locations. If you stop and think about it, what is language in general? All language is an abstraction layer to allow for easier information transfer of knowledge between humans. Programming languages are the same thing. They're symbolic abstraction layers to allow easier control and configuration of instructions and information flow to computers. So here's a basic code example to demonstrate symbols. You can see this is a very simple program. It doesn't even have any functions. It's just running in main, but this is all we need to see. The int here is a symbol. Number, it's a variable name, that's a symbol. Test string, another variable name. Cout here is a function. Return is an instruction. So you can see every single piece of code that you read as a human, you're actually reading a symbol that translates to something else for the computer. Now that we understand what a symbol is, it frames code in a different perspective. Let's ask a question here. Why does the computer actually care that you named your variable X or Y or number, or in Unreal, if you name it PC for your player controller? All of that is actually completely meaningless information for a processor. So we have symbols that constitute programming languages in order to make programming easier for us as humans and link between the higher level abstraction of our source code and what eventually becomes binary data. This code is a hypothetical example of what C++ might look like without symbols. This is not meant to be realistic, but it's just to further emphasize what symbols are and why we need them. So as you can see, the one at the top is quite a bit preferable to the one at the bottom. Without symbols, variables would need to be referenced by memory addresses or just arbitrary memory locations. Functions would lack identifiable names, making it really difficult to call or reference specific blocks of code. Developers would likely need to rely on some convoluted method or error-prone method to be able to execute sequences of instructions. You can immediately tell that the code readability would be terrible. You're looking at basically a wall of numbers rather than human readable language. Programs would be just overall very challenging to comprehend because of the absence of any named elements. And then from a maintenance and debugging perspective, it would be terrible. Without any kind of clear identifier for variables and functions, debugging and maintaining the code would be very cumbersome and very frustrating. Developers would have a lot of struggles when it came to tracing down issues, understanding the flow of the program execution, and just generally making changes to the code base. So you can see where I've highlighted a few places here where the code corresponds. And again, just remember, the one at the bottom is a hypothetical example. All of this is just to show that symbols are the key aspect of what makes a programming language useful and why it makes it easy for humans to use to control the computer. And now that you understand the general concept of a symbol as it relates to programming, finally we can address debug symbols, and the understanding of those will naturally fall into place. When we say debug symbols, from analyzing the build process, we now know that this really refers to PDB files. But we also know that the term symbol itself is actually the more important piece of the puzzle here. When we do normal builds in release or shipping mode, all of the program symbol data is lost. But we don't care about that since we only have an interest in the final performance of our built executable. But when you need to debug your program, you want to be able to run the debugger and synchronize your code along with the program execution in a way that lets you understand it. So to enable that to happen, the debug symbols contain the following information about the source code. They contain the variable, function, and class names, type names for all types, which includes not only standard types, but functions and exceptions and things like that, line numbers, file names, scope information, meaning if the variable or function references only in a specific code block or if it's globally accessible, and size information as well. And so that's why debug symbols are necessary. They contain this information that forms a bridge between the compiled binary code that the processor will run and the human readable source code by storing a lot of information about the code before it was compiled. Debug symbols also allow for having a useful stack trace. If you aren't familiar with that term, a stack trace is basically a list of all the different functions that were called in order to accomplish some portion of a program's functionality. Typically, the context where you're going to encounter a stack trace is either going to be due to a crash and you're trying to figure out where that originated, or just while debugging and looking at what functions were previously called to get to a certain point in the program. The majority of us have probably regularly seen a stack trace presented to us by Unreal Engine in the form of the crash reporter. If we look up some examples of the crash reporter, we can see the stack trace and how debug symbols play a role in it. So now I've gone to Google and just typed in Unreal Engine crash reporter, and I picked out two examples that we're going to compare to see what impact debug symbols have on a stack trace. Now you'll notice this stack trace doesn't look very useful. It has a list of something here, and then it does have one single line that tells you there was an assertion failure which would have caused your program to stop, and it happened on class.cgp line 1499. That alone is okay. It can be useful sometimes that's all you need. But what does all this mean? This is the operating system trying to tell you what happened leading up to this assertion failure. But it can't do it because there was no debug symbols loaded. So the final program executable that's running has no link back to the pre-compiled source code. So all the operating system knows here is that some module named UE4 editor core UObject was executing, and that led into Kismet, which is another name for blueprint, and so on and so forth up into the assertion failure. If all you need is just that one line, then sure, this is fine. But what does this look like when we load debug symbols? So now look at this example. It's a little blurry because I pulled it off the documentation page of one of the older Unreal Engine documentations, but it still serves the purpose we need. You'll notice immediately there's a big difference here. The difference being now, instead of just a list of generic module names leading up to the actual crash, we have function names, the file that they were in, and the line that they were on. Now this is cut off a little bit, but it's not really important. The main thing to know is that the debug symbols form that link between your final executable and your source code. And so with debug symbols loaded, rather than just a list of generic modules, which is all the operating system can see, with the symbols loaded, it now knows that do task executed, execute tick, tick actor, and so on and so forth, all the way up into the crash. It looks like they probably made this custom code because it's kind of got a funny little name here to cause a crash on purpose, but that's fine. This will always be in this kind of format and present you with this same information as long as you have debug symbols loaded. You can see here that it has the line number, the file name, the function name, and the class that called the function. Stack traces always grow from bottom to top. So whatever's at the top is the most recent thing that happened, and at the bottom is the oldest thing that happened. And so this is just a really simple way to show how just by simply having debug symbols loaded, you start to get more information that helps you troubleshoot and solve errors in your code easier and more efficiently. Now there's one more thing I'd like to show before we move on related to debug symbols. If you go into the launcher and go to library, where you have your engine installation, if you choose this drop down here and go to options, you can see now this is where you actually install the editor symbols for debugging when you install the engine. Because like I said before, we're only installing one specific version of the engine. It's not going to change as we use it. The only way it changes is if we, one, build it from source, or 2, download and install a new version. So because this one version was built by Epic, they also built the debug symbols for it, and then they can let us install those. Now, you'll probably notice, or you may have noticed in the past, that these debug symbols are not small. But now, because we've covered what is in them, what they actually are meant for, it should make sense. There's a lot of source code in Unreal Engine. I don't know the exact number. It may be in the millions of lines of code, but it's definitely not small. We all know that. And so now when you think about it, for every single symbol in Unreal Engine, if we need to be able to install the debug symbols for those, that's almost going to be a one-to-one copy of data. And so that's why the core components are about 34 gigabytes, and the editor symbols for debugging are almost the same size. They're only a few gigabytes smaller. It should make a lot more sense now that you know what all goes into them. It is definitely kind of frustrating sometimes. I've seen people mention this before on Discord and stuff, to have so much space be taken up by these debug symbols. But because they give you so much flexibility and ability to troubleshoot and debug your code, I think the trade-off is always well worth it. At this point, you should hopefully be forming a chain of events in your head for how debugging happens. The build generates the debug symbols and object files, which contain the path to their associated PDB files. Then, the linker ties it all together when it creates the executable, and that path to the debug information then allows your IDE to know where the PDB files are in order to extract the necessary information from them to debug through your source code. I said that the linker ties it all together. In order to do that, the linker references something called a symbol table. The symbol table is a table where all of the relevant symbols in an executable are aggregated. It's used in all build configurations, not just in debug. The linker uses the symbol table as a reference when performing its linking process in order to resolve symbols across all the different object files or libraries that are brought in during the build phase. The linker needs to resolve them in order to establish the connection between the compiled source code and any objects that the source code needs to use. Remember the example that I said earlier about the character class needing to interact with the inventory class. When the linker iterates through the symbol table, if it encounters a symbol that it cannot find a definition for, this results in an unresolved symbol error. So let's take a look at an example of that. So this is a post I found on the Unreal Engine forums where someone encountered a symbol error and they were stuck and they asked for help. So what you'll notice here is he said, I'm trying to play my level sequence using this piece of code, but when I build, I get this message. In the past, without any knowledge of build processes and linkers and symbols, this error probably looks like complete gibberish to people. It did to me when I was first starting out and learning. But when you start to understand the process, you start to understand that there's nothing in this error that is gibberish. Every single piece of it has a purpose. And already, I hope that when you see this, this now makes sense to you based on the information that I've been showing. Because we have here, okay, we have an error. This is the error ID. Unresolved external symbol. Notice it specifically says external. The reason being is that this symbol is not defined in the person's project. Remember how I said the linker pulls in external objects to try to resolve any symbols. It knows this symbol is not defined in the project, so it knows that it's supposed to be external. But as it went through its process and iterated over the symbol table, it never found a definition for this symbol right here. This play function from uMovie Scene Sequence Player. So it immediately throws an error, unresolved external symbol. It tells them what symbol it's trying to find. And then there's other information here that even makes it more clear. This is what is called a storage specifier when it says decal spec. You can read about this on Microsoft documentation. It's not super important for right now. But the key thing to know is that this says DLL import. So what this is saying is that this symbol has been annotated as being imported from a DLL. That is why it's known that it's an external symbol, because it knows there's some external DLL where this resides and we were not able to find it. The cdecal here, that's another thing that's worthwhile to read about if you find the whole build and compilation process interesting. But what that is what's called a calling convention specifier. This is kind of more in the computer engineering realm of things, but all functions have a calling convention that will tell the system how it's called, how its arguments are allocated, and also how to handle the memory both when that function is called and after it exits. And so that's what that is saying right there. That is a calling convention specifier. It then goes on to say that it's referenced in this function, which is probably something in his project now. And then he says, my build.cs contains this line to configure the modules. And then as you can see, somebody came along and told him, hey, you are missing a module. And he posted and said, I added movie scene into the module names and it fixed the problem. So this is a very straightforward case of the linker failing to resolve the definition for a symbol during the build process. Because the module was not added to the list of module names in the project, the linker had no ability to go and look for it. And so it iterated through everything it had. It iterated through all these modules. And at the end of the process, it never found a definition for this play function. So the only choice left is to say there's an unresolved external symbol. So this is a very common error. I'm pretty sure every single person has run into this at least once in the context of programming, whether it be game programming or normal programming. But my hope is that now, by breaking down each piece and understanding what symbols are, this now makes perfect sense to you. So now I want to give a little bit more amplifying information about symbol tables. This is a very simplified version of a symbol table, but it does well to illustrate the intent of it. It shows how all the functions, their scopes, and all the symbols, including the function arguments, are listed. The main thing to take away from this is just to realize that when it comes to external symbols, they must all have a definition that can be found somewhere, even if it is in an external DLL that your program then gets a stub for, as we saw in the build process slide. So this almost wraps up the last of the information I wanted to present in these slides. But before I go towards the conclusion, I'd like to do a short live demonstration to show what a real symbol table looks like. So now I have VS Code pulled up, and I have a program here that I made, again, for experimentation to figure out some code. In this case, the code that I was experimenting with was this weird syntax you see here. This is actually valid C++ syntax that declares a function that will return a pointer to an array of a specific size. So I had never encountered that before. So when I saw that, I made this little program to be able to experiment with it and figure out how it worked. The reason I'm in VS Code is because I'm actually using WSL. WSL stands for Windows Subsystem for Linux. It's great if you ever need to use Linux, but you don't want to have a dedicated Linux computer. It allows you to run an actual Linux distribution on Windows. And then if you have VS Code, it connects directly to the WSL instance and allows you to browse files and edit code and everything. So it's extremely convenient. The reason why Linux is more useful for this demonstration is because Linux has some pre-packaged utilities that allow you to extract different data from built executables and examine it. So in the directory I'm in here, I have the sized array.cpp, which is the one we're going to work with. Now I'm going to compile it using the G++ compiler. And now what I'm going to do is I'm going to give it some flags that will simulate a release build. We're using the capital O flag because that stands for optimization, and that's going to tell the compiler to do as much optimization as it can. The 3 represents the level. You can do O1, 2, 3, and then there's some other things you can optimize for size, just like how we saw earlier in the build configurations. But with O3, it's going to do a lot of optimizations, and so this is equivalent to doing a release build. So that compiles really fast, and now if I look at it, here's my executable. It's only 17 kilobytes in size. Now let's change the compilation flags and let's give it the G flag. The G flag represents debugging, and it will generate debug symbols. And again, the number is a level of, I guess you can consider it intensity, where G3 is going to try to remove all optimizations and generate as much debug information as it can. So I'm going to change the name of the output here to sized array debug. And now you'll see we have the 2 executables. Now right away, look at the size difference between these two. This is exactly what I was referring to earlier, showing the engine symbols when I said that they contain a lot of information. And you can see this so clearly here. The optimized version is almost 10 times smaller than the debug version. So those symbols really make a big difference, especially on Linux here, where your final executable is actually embedded with all the debug information. Now we can look at the actual symbol table of these executables, and we do this using a utility that's built in called object dump. Now object dump can take a couple different flags to tell it what to do. The -t flag is the one that tells it to dump the symbol table. So I'm going to get the symbol table from the optimized executable. And this is the real symbol table that was used when that program was compiled and linked. It's even labeled for us, symbol table. You have a list of addresses here. You have a bunch of different specifiers and a bunch of other different information that could be useful depending on what you need to do. The symbol names themselves are over here on the right, but you'll notice they look a little bit hard to read. There's these letters and underscores and things appended onto them. Some things are still pretty readable, but then some other things are just a little bit jumbled up. So there's a reason for that, and the reason is something called name mangling. So name mangling is something that happens in C++ to account for the fact that we can do function overloading and have multiple different functions name the same thing. The compiler needs a way to easily differentiate those symbols on the back end. So it mangles the names to give them all very unique identifiers. You can see here, here's my sized array pointer function. And in the symbol table, it's got an underscore Z13 added onto the front of it. So it just mangles every single name just by default. But if we then modify our function call here to give the capital C flag, now you'll notice the names are not mangled anymore. So that's all that flag does. The capital C flag just disables name mangling. Now we can read everything and see all the symbols that were used. These specifiers in this column represent some information such as, is it a local symbol? That's what the L would be. Is it global? The G. And there's a bunch of other ones. If you're interested in learning about that, you can search for the Linux manual page for object dump, and it has a legend in here that explains what all this stuff is. So now let's dump the symbol table for the debug version. Because we know there's a lot more information in debug symbols, you can see that this symbol table is a lot longer. There's not too much that we really need to see here. I just thought it would be neat to show an actual example of a symbol table to be able to show exactly what the linker uses on the back end when it's creating your program. Now there's one more thing that's interesting to look at, and that's the actual sections of the program. So there's a utility called readelf. In Linux, the final output format of executables is the ELF format. So using the readelf utility, we can actually look at the different sections in those executables. So I'm going to first look at the optimized version. You can see in the name column here, these are the names of the sections of the executable. And again, some of it matches the symbol table. We have the data section, the BSS section, there's a section for comments. There's the symbol table itself, it gets its own section. And then there's a bunch of other things in here. So now what's interesting with this is, if I now dump the sections from the debug version, you can see that all of this debug information gets its own sections in the executable. And that matches exactly with how we said Linux embeds the debug information. This same information would come out when you compile a Windows executable in debug mode, except it gets put out into the PDB files. And what's interesting to see here is that it has an info section, it has line for line numbers, strings, macros, and a couple of other things. So hopefully this was interesting, and it just shows you that the debug information is embedded in Linux. But really, the main thing to emphasize here is that debug symbols take up quite a bit of space. That was the most striking thing for me when I did this experiment, was just the sheer size difference between these two. And this is a pretty small program. So for it to be 10 times larger just due to debug information, that's pretty interesting. The whole goal of this presentation was to show that using the debugger is your most powerful form of debugging and troubleshooting your code. But there is a time and a place for print statement debugging as well. Print statement debugging is what most people do when they're just starting out. It's exactly what it sounds like. You just put print statements everywhere to be able to print data to the console or to a log or to put it on screen, and then you use that for your troubleshooting. In normal coding, print statement debugging is useful, but it's actually much more useful when you're working with Unreal. The reason for this is that with Unreal coding, you have lots of numerical parameters that define the behavior of things. For example, in the character movement component, you have things like walk speed, jump height, and all kinds of things like that. So being able to print those values to the screen or to a log is very useful sometimes. So I just wanted to add a slide here to mention that since print statement debugging is a valid and often useful form of troubleshooting and debugging, the main thing to remember is that you shouldn't use it as a crutch, but you should learn to use a combination of the real debugger and print statements until being able to recognize the most useful tool for the job feels like second nature to you. The most effective troubleshooting will come from being able to use a combination of the two. And that concludes my presentation. The next videos in this series will cover debugger controls to show you how to actually set up and run the debugger, and I'll also be demonstrating some live debugging examples using one of my projects. I hope this information was useful, and feel free to let me know if you have any questions or feedback in the comments.